It was the year 1822 when a guy named Babbage started to work on a weird kind of machine. He called it a differential engine. And that was a physical machine to solve polynomials. A few years later, 1847, another guy called George Boole created the basis of something that we know today as the Boolean algebra. And that was the dawn of computing. To be more accurate, that was the dawn of classical computing. Things started to pick up really quickly after the 1940s, the 1950s, and all of a sudden, starting from these physical, mechanical machines, we find ourselves in the era of transistors. We find ourselves in the era of high-speed compute. Of course, we started with a few transistors, and then we went quite quickly to literally millions and billions of transistors. And from this, we went even quicker to this, and then to this, and then to this. And it's such a great time to be in IT in this particular decade. Think about the computing power of the CPU. Think about the computing power of the GPUs. And think about what you can do when you start creating programmable hardware, like an FPGA, or even a hardware tensor unit, or even an ASIC, an application software integrated circuit. But let's just try to step one step back and think about this. This looks like an enormous quantity of computing that we have at our fingertips. Think about the combined power of the public cloud provider data centers. Think about combining the computing power of Microsoft, of Amazon, and of Google. Right? It seems huge. And this conference and many other conferences are standing proof of the amazing stuff that we can do with today's computing power. Yet there is a problem. The problem lies in the situation where we need to solve problems that are exponential. The solving of exponential problems, even with today's unbelievable power, still eludes us. And there are lots and lots of problems that cannot be solved. I like when I see in the news like supercomputer X simulated a nuclear explosion. And you go like, dude, the times that we live, right? It's like we're simulating nuclear explosions. The reality is that that supercomputer simulated a super simplified model that resembles remotely what happens in a nuclear explosion. Turns out nature works in a way that even with today's classical computer resources, we cannot keep the pace. One of the big problems that humanity faces today is inventing the right materials and the right substances. And Dr. Marcus, in the keynote, talked about that amazing molecule, which we call the Femoko molecule, that once it is understood, could replace our ancient technology for producing fertilizers. I give you an even simpler example. What if I want to model the behavior of a system that contains 30 electrons. To keep track of the states for that model, I will need 2 to the power of 30 numbers, right? Suppose the number is a tiny number, like a byte. I would still need 2 to the power of 30 memory locations just to track all the states, because, of course, you need to track all the states as they occur with different probabilities. Now, if you go from 30 to 100 electrons, you're already surpassing that combined power that all the data centers in the world have. And if you go from 100 to as little as 300, you've already surpassed the number of particles in the known universe. So, turns out, nature works in a way that classical computing is not really capable of simulating, which is in itself an amazing thing, right? And the promises of quantum computing, computing that works based on how nature really works, are just mind-blowing. New materials, new substances, improved algorithms are some of the promises. But because I'm kind of a realistic guy, I will emphasize on the word promises. They are not certainties. We think today we could use quantum computing for all of these. There's a good probability that we will be able to use it, but these things are not yet certain. So, let me start with the very, very beginning. The humble bit. The humble bit in classical computing has only 2 possible states, 0 or 1. And turns out there are very limited number of operations that you need on a bit or on multiple bits to sort of implement any kind of algorithm in classical computing. The equivalent in the world of quantum computing is, ta-da, the qubit. Now, the qubit is a weird animal because it can have 2 states, a 0 and a 1, but it can also have any linear combination of those states described by 2 complex numbers. The only condition they have to meet is that their norms added should be 1. There's a saying that I love so much, which says, the universe is a complex thing. It has a real part and an imaginary part. Now, the first question I always get from developers, from IT people, even from non-IT people, is why? I mean, why is the qubit an alpha and a beta? And why are they complex numbers? And why the sum of their squares norms should be 1? Why? Why don't we have 3 numbers? Why shouldn't they be real numbers? Let me tell you a story. I am considering myself a very, very fortunate man because life had taught me humility in more than one way. The one way that I want to tell you about is, it gets back to my first year in college. I was what you could call a calculus hotshot. I thought I knew calculus, right? So besides calculus, we were forced to study two other things. One was probabilities. The other was statistics. I hated them with all my guts, right? Fast forward 20 years, I work mostly in AI and for a few years in quantum. Guess what? When I wake up, I dream probabilities and statistics. When I go to sleep, I dream probabilities and statistics. It's a weird lesson that life has taught me. Now, about 15 years when I started to study quantum mechanics, I was really not able to get past the first chapters. I watched one of the, I believe, the best introductory courses in quantum mechanics, which is Professor Leonard Susskind's course at Stanford. I was never, ever able to get past chapter 3. I'm like, am I stupid? Like, I know math, right? Now I already know probabilities and statistics. How come I can't understand this stuff? Until I met a professor from my hometown university, a professor of physics, who enlightened me. It's like, dude, you know why can't you go further with this? Why? Because you try to picture that information in your mind. Forget about that. Go with the math. I was like in shock and awe. I was like, how that can be possible, right? Now back to the question of why is this like this? Well, it is because of some of the fundamental principles of quantum mechanics, which we call postulates. They are the kind of thing that you observe in nature, but you cannot explain. They are because they are. That's like mind-bending, right? So the first postulate, it says that any physical system in the nature can be described using a vector space of complex numbers. Right? And this in itself is amazing. And it is amazing because of this. This means that if a system has one state and can have another state, it can have any linear combinations of those states. So back to the humble qubit, this means that a qubit can have an infinite number of states. Welcome to the world of quantum computing. And that's just the beginning. The second one is even more interesting. It says that if you want to observe a system in nature, the way it evolves can be described by what we call a unitary operator, which is, by the way, nothing else than a matrix that has some properties. And here's another amazing thing about quantum. It is described by linear algebra. Turns out, if you remove the restriction of linearity, you get into the weird stuff like time travel, which at the moment we think it's not possible. This is why we use linear stuff. Now, the other cool thing about this is that it is a unitary transformation, which means every single operation in quantum is reversible. This is one big step from classical computing. Think about the OR gate. The OR gate on bits is an irreversible operation. Given the result of it, you cannot tell for sure what the inputs were. In quantum, everything is reversible. Turns out, therefore, some of the states of this system, if you apply that operator, you get the same state multiplied with a number. And these are fundamental in quantum. The number is called the eigenvalue. The state is called the eigenstate. Now, why are they so important? Is because of this. The only result that you can get when you measure a system is one of the eigenvalues. Which means, getting back to the humble qubit, there's no way to find the state of the qubit. The moment you measure a qubit, it will either yield the 0 state or the 1 state, and that's all. And the qubit itself will collapse into one of those states, and no matter how many additional measurements you do on the qubit, you will always get the same initial value. We call that the collapse of the state. So you might already be a little bit puzzled. It's like, dude, these things have an infinity of states. They cannot be measured, yet we're talking about doing computing with these things, right? Isn't that like just simply amazing? Now, here's the other postulate. And again, all these things are derived from experiments, from what we observe in nature. There is no proof for these. There's only a general belief today that they are true statements. So this postulate says that when you measure, for instance, a qubit, you will get the 0 state with a certain probability, and you will get the 1 state with a certain probability. And of course, if you add the two probabilities, they will yield 1. Which means that if you would really, really want to learn about the state of a qubit, getting the accurate values, you would need to do what? An infinite number of measurements on an infinite number of qubits that are set initially in the same state. So good luck creating algorithms with that, right? It's amazing. And this is the one that I've already mentioned, right? So immediately after you get the value, the system collapses to one of the fundamental states. And finally, this is what you sort of hear and see every time somebody talks about quantum, right? The postulate simply says that the time evolution of the system, meaning applying that unitary transformation to a state, getting a new state, and then applying that and getting a new state and so forth, preserves what we call the normalization of the state. You will hear many, many times the state being referred as a ket vector, or simply a ket. Turns out that this implies the equation at the bottom of my slide. Don't worry if it looks like alien sort of wording to you. That is what we call the Schrödinger equation. That is the fundamental of quantum. So let's get back to the question of why. It should be a little bit clearer now why we design the entire logic of quantum computing around this model. Basically, what we are saying is that qubits live in a two-dimensional space that is defined by two complex numbers, alpha and beta. And the only thing needed to have a valid state is to satisfy the condition of the sum of the square of the norms of the complex numbers should be 1. Which in turn means that this space turns out to have these two eigenstates. And by convention, we name them the 0 states when alpha is 1 and beta is 0, and the 1 state when alpha is 0 and beta is 1. And the qubit can have any linear combination of these states. So looking at this slide is like, dude, that is so abstract, right? It's like, ugh. Well, it turns out there were folks that invented a way of looking at this in a different way, which is more visual for the human brain. And that is called a block sphere. Now, let's go back to the definition of the qubit, right? Alpha is a complex number, which means it's defined by two real numbers, right? The real part and the imaginary part. Beta is a complex number, which means it is defined by two real numbers. So it occurs that a qubit is actually defined by 4 real numbers. But because there's a relationship between those 4 real numbers, it turns out that the qubit can be defined by 3 real numbers. And those 3 real numbers are actually points on the sphere that has radius 1. So now it becomes, in a more visual way, obvious why a qubit can have an infinity of states. Think about state 0 as being an arrow from the center of the sphere to the North Pole. That is state 0. Think about state 1 as being the arrow from the center to the South Pole. That is state 1. Now imagine an operation on the qubit being defined by simply moving the tip of the arrow. Like this, like this, like this, like this, like this. So in a visual way, an operation on a qubit is simply moving the tip of the arrow. But because the sphere has an infinite surface in terms of points, turns out you can have an infinite states for your qubit. And even more than that, which is even more sort of disturbing, you can have an infinite number of operations on the qubit. Those operations, we will see in a moment, are called gates. So, turns out, you can have operations on a qubit. And because the qubit is in a two-dimensional vector space, the operations will be 2 by 2 matrices. If you multiply a 2 by 2 matrix with a two-dimensional vector, what you get is a two-dimensional vector. All of these matrices that I'm showing you here are matrices that satisfy the requirement of leaving the qubit in a valid state after they are applied. The ones at the top line are what we call the Pauli gates. What they do, if we go back to the block sphere, they simply flip the state on one of the fundamental axes. So the X gate, what we'll do is we'll take the arrow from this position, and when applied, we'll flip it down. The Y gate will take the arrow from this position, and it'll flip it the other way. And of course, the Z gate will take it from here and get it there. These are some fundamental gates. Now, the fourth one is the one that made Einstein be so upset. That gate is what we call the Hadamard gate. And the Hadamard gate puts a qubit in a state that we call a superposition state. Because it puts it in a state where if the qubit is measured, you will get 0 or 1 with equal probabilities, 50-50. So think about this. In a visual way, basically what the Hadamard gate, it puts your qubit, the arrow something like this. So when you measure, it will go either like this or like this, 0 or 1, with equal probabilities. If you take a qubit, apply the Hadamard gate to it, and then you measure it, and you do this enough times, you will get roughly about half of 0 states and half of 1 states. Why did this make Einstein very upset? I will tell you in a minute. Turns out there are two other gates which I'm not going to enter into too much of detail. The S gate, or also which we call the phase gate, and the P/8 gate, or the T gate. We will see in a moment why these gates are important. Now, just think about it. All we've talked about so far is one qubit. This is one qubit, right? Let's see what happens when we talk about multiple qubits. So, one qubit will always be in a state defined by two numbers, say alpha 0 and alpha 1. If you take two qubits, you will already have a number of 2 at the power of 2 states, meaning 4 states, defined by alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1. The squares of these will still need to obey the rule that their sums should be 1. Go with 3 qubits. You will have 8 states. Go with 1,000 qubits. A system with 1,000 qubits can model 2 at the power of 1,000 states, which gives you a little glimpse on the unbelievable, raw, hidden, and I emphasize hidden, power of quantum computing. So, this is the picture that Professor Marcus showed in the keynote, and he said, you can tell these two folks are really, really upset. And they were. And just as a side note, this is another example of how life can teach humility, even one of the greatest geniuses of all time. The quantum effects that were predicted by his genius theory were looking totally unrealistic and unbelievable to Einstein. In fact, until the end of his life, he tried many, many times to prove them wrong. He could simply not believe that nature could work in a way that is fundamentally based on disorder. Yet this is how it works. And the reason why he was upset is this particular state of 2 qubits. You can see here that alpha 0, 0 is 1 divided by the square root of 2. Alpha 0, 1 is 0, hence we don't have it. Alpha 1, 0 is 0, hence we don't have it. And alpha 1, 1 is 1 divided to the square root of 2. This is a state of 2 qubits that is called a Bell state. Sometimes we call it an EPR pair. EPR stands for Einstein, Podolsky, and Rosen, who wrote a famous paper trying to show that this cannot be real. Yet it is. The popular name of this is entanglement. These are 2 entangled qubits modeled in a mathematical framework of quantum computing. Why is this like brain explosive? It's because if you entangle the 2 qubits and you separate them apart, say by 10,000 kilometers, and you do something with 1 qubit, it instantaneously happens to the second one as well. And this has been already proven by countless experiments. Turns out there is somehow a connection between the 2 of them, which looks to be instantaneous. So the immediate thought that you can have is, dude, this is the way to pass the speed of light. This is the way to communicate faster than the speed of light. Well, Mother Nature has surprises for you. It is not. Turns out there is a fundamental theorem, which we call the no-cloning theorem, which says with 2 entangled particles or 2 entangled qubits, you cannot transmit any kind of quantum information unless you also transmit some classical bits. Transmitting classical bits is still subject to the speed of light. Yet, we can do some amazing things based on entanglement. Now, might be a good moment to move to gates that operate on 2 qubits. So far, all the gates I've shown were gates operating on 1 qubit. They were matrices of 2 by 2. Obviously, if you need to operate on 2 qubits, you will need a matrix of 4 by 4. This matrix is a fundamental matrix in quantum computing and the fundamental gate, which we call the C0. Or in other words, it is the controlled NOT gate. What it does is described at the bottom of my slide. The inputs are 2 qubits. The gate works like this. If the first qubit is 0, nothing happens to the 2 qubits. If the first qubit is in the state of 1, the second qubit is flipped. That is an apparently simple C0 gate. Well, turns out the Adamard gate plus the C0 gate are the gates with which you can produce entanglement. So, all theory, very nice, very interesting, hopefully, but time to see some stuff in action. Let me just duplicate my screen and open what else than Visual Studio, of course. Are folks in the back okay with the size of the font? Yeah? Thank you. So, turns out Microsoft created what we call the Quantum Development Kit, which enables us to do quantum programming in a language called Q#, using a quantum simulator. Now, because we're using a quantum simulator, of course, the number of qubits that we can use is severely limited. Yet we can do some amazing stuff with this. Let me show you. So here's the way in which a quantum program looks in Q#. Obviously, it's basically a .NET program, console application. So what I do in the first place, I'm initializing a quantum simulator, which is basically the equivalent of a quantum computer with a limited number of bits. And then what I will do is I will repeat 100 times this operation, measure 1 qubit. And then I will simply show the results, and I will show you the frequency of zeros and ones. Now, obviously, this is no news for any programmer, right? So the fun part is actually here. Let's take a look on how do I do this. So what I'm doing is I'm requesting from my quantum canon, and a bit later we will talk about the canon. It's not the kind of canon that you would think, right? So I'm requesting from my quantum canon 1 qubit, basically an array of 1 qubits. Then I'm applying the Hadamard gate on the qubit, which means I'm putting this qubit in a superposition where both states, 0 and 1, occur with equal probability, 50%. And then simply, I'm measuring the qubit. What happens the moment I measure the qubit, it collapses to one of the states, 0 or 1. So at the end, what I'm doing is if it collapsed to the state of 1, then I'm flipping it back to the state of 0. There's a fundamental rule in programming with Q#. Every single time, you need to return your qubits in a 0 state. You get them in a 0 state, always return them in a 0 state. Sound kind of like reference incrementation in the old days, right? Kind of. Well, and I will run this multiple times. Let's see what we get. So let me run this. Because we have a small number of qubits, it runs on my machine. So here's what I've got. The results of the measurement are I got 51% of the time the value 0, and 49% of the time the other state. And the reason why they are not 50 is because I did a very small number of measurements, and because the random number generator on my computer is not really a random number generator. It's actually a pseudo-random number generator. So that's why you don't get all the values. OK, let's go into a little bit of a more detailed approach. So now the next thing that I'm going to do is I'm going to measure 2 qubits. So I'm requesting 2 qubits, and then I'm applying the same Hadamard gate on both of them. And then I'm measuring them. And this is a nice operation that I have in the quantum SDK, which says M reset Z, which means measure and then reset the qubit. So I don't need to check the condition that I checked before. So basically, when we run this, I'm going to run again the first step, of course, and then I'm going to run the second as well. Here's what we get. Pairs of qubits and there's absolutely no connection whatsoever between their states. Right? You can see that you can have 0 or 1 or 0 or 0 and 0. This is because applying the Adamant gate to every single qubit created a superposition state which is independent of the other. Now here comes the fun part. Next thing that I'm going to do is I'm going to request 2 qubits, but this time, and take a close look to this. I'm applying Adamant gate to the first qubit, and then I'm applying the C0, the control NOT gate, to both qubits. What happens is they will be in an entangled state. So now when I do the measurement, guess what? The states match perfectly. And that's because they are entangled. I haven't set the state of the second qubit. I just applied the C0 gate. And if you want to go a little bit further than that, let's just bump up this a notch and get crazy. Let's do this. So this is another gate. This is a more composed gate where I do a rotation based on an angle. And I only do the rotation on the second qubit. So think about it like this, right? Initial qubit set like this. Then I'm entangling them. And then I'll apply a rotation for the second one, say something like this. What happens when I do this? This is entanglement. And of course, if we run it again, we will get the result that we are expecting. If my Visual Studio agrees to do it, and it does. Sorry about that. So, oops. Apparently, there was a problem in my simulator. I'm very sorry about that. Let me do it again. OK. So as you can see, in the third case, I still have the same states. This is truly, of course, it's a simulated one, but it's a simulated demo of quantum entanglement. Isn't that just amazing? So let me continue, because there is some even more interesting stuff down the road. Now, turns out that if you take this set of gates, H, S, C0, and P divided by 8, or the T gate, this set of gates is a universal set of gates. Which means that with only these gates, you can actually create any operation in quantum computing. And this is a fundamental result. This is why we actually have quantum computing. Because if you cannot find a set of gates, it's very similar with what happens in classical computing. If you cannot find that set of gates, then you cannot create complex algorithms. Everything I've showed you until now is perfectly useless. Right? There's absolutely no application for what I've shown you so far, unless you can build on top of this and create complex things. And without this fundamental thing, you cannot do that. So here's another moment for reflection. I want to do an algorithm. I want to implement an algorithm. Yet, I have a computing framework, quantum computing, where I can set initial states for my qubits. I can change those states, but I cannot read them. Because the moment I read them, they collapse. So good luck designing quantum computing algorithms with this. It's like you're working with a black box. It's like, how many of you do any kind of work with databases? Right. Imagine that all you can do is set the initial state of the database and then do operations on it without ever reading the database. And expect to obtain the correct result. Is that cool or what? Right? Well, this is the challenge. This is the challenge for implementing advanced algorithms with quantum computing. So now is a good moment to get into a real demo. And this real demo is about search. Suppose I have n entities, and for the sake of simplicity, let us suppose that n is a power of 2, right? And I have a function that gets as input an entity and gives me 1 if that entity is the one I'm looking for, and 0 otherwise. And suppose that function gives me a 1 only for a single entity. This is a sort of a formal definition of a search problem. Now, in classical computing, if I choose randomly one of the n entities, what is the probability of getting the one that I'm looking for? Is 1 divided by n, obviously. Turns out, with quantum computing, you can get the same result, but not with a complexity of n, but with a complexity of the square of n, which is in itself a sort of unbelievable result. Every single time I talk about this algorithm, I get people looking at me like, dude, what's the catch? Right? Let's take a look. And I won't go into the details. I'm going to only discuss about the principles. Nevertheless, it's absolutely impressive. So let me go back to my Visual Studio, and let's switch gears. And I'm going to do the following here. So I'm going to set up, of course, I'm creating my quantum simulator. And then I'm going to do a random search without any quantum improvements. And just remember this number of iterations, which is 0, right? And I'm going to use 3 qubits, which means that I can simulate searching in what? In 8 entities. Now, this might seem like, dude, why do we want to search in 8 entities? Well, imagine that when you have 1,000 qubits, you can search in 2 to the power of 1,000 number of entities, which is kind of mind-bending. So For the purpose of the demo, I'm searching in 3 entities. And of course, the classical success probability is 1 divided by 8. And I'm going to repeat the process 1,000 times so that we can get some statistical relevance out of it. And what I'm going to do is I'm going to run this operation called apply quantum search. We'll get to it in a moment. And then this will return a result which will give me a 1 or a 0, meaning that I found or I have not found my entity, and then the state of that entity that I was generating at that moment. And of course, what you would expect running this is you would expect to find the right entity every 1 cases out of 8. So let's go a little bit to apply quantum search, because this is the real juicy part of it. And without getting into too much detail, this is apply quantum search. So what I'm doing here is I'm allocating n+1 qubits, and 1 qubit will be an interesting one because I will use that to be what we call the marked qubit. The marked qubit will be in a state of 0 if the other qubits do not represent the entity that I'm looking for, and will be in a state of 1 if I have found the state that I am looking for. And then I'm going to call quantum search. I'll get to that in a moment. And then I'm going to simply return the results. I'm going to measure the marked qubit, and I'm going to measure the rest of the qubits and return their states. And at the end, I simply reset all my qubits, because, of course, the rule is you have to return them in a 0 state. So what does quantum search? Here's the amazing thing. This function that I mentioned that gives you 1 if the entity is the one you're looking for and 0 in the rest of the cases is called an oracle. What the quantum state does, it initializes, it allocates n qubits, and then initializes all of them with an Hadamard gate, meaning that when you read them, you either get a 0 or a 1. So basically, I'm allocating a random bit string generator of length n. And then I define my oracle, just for the sake of the demo. My oracle is basically this operation, which says the following. I will only mark the marked qubit if the rest of the qubits are in a state of 1. So basically, the entity that I'm looking for is an entity that has all n qubits in a state of 1. It's very simple. I'm looking only for one entity. This is the function that returns. And getting a little bit back to quantum search, this part is the amazing part. And in the first part of the demo, I'm going to run with 0 iterations, so this part won't run. Let's see what happens. It's quite expected and quite obvious. So you can see here, the theoretical probability is 0.125 because it's 1 cases out of 8. And as I run through my states, as you can see, the probability sort of goes toward that. And in fact, I only display here every 100th attempt. And unfortunately, in none of those attempts, turns out that I found the state that I'm looking for. But there are attempts where obviously I found it because my probability is close to the theoretical probability. So this is an example of how quantum does not improve anything. Right? Right. Now let's do some magic. Now, in the second part, I will run with multiple iterations through what we call a Grover transformation. Oversimplifying things, what happens is I get that initial state, but instead of trying to see whether that state is the state that I'm looking for, I'm doing the Grover iterations on it, meaning I'm applying a set of smart choices of quantum gates, which increase the probability of making the result of that the right result. It's like, holy shit. Let's run it. And we're simply restricted here by time, and that's why we can't get into the nitty-gritty details of this. But there's nothing funky here. This is real. So now I'm going to press a key, and I'm going to do the same thing, but that initial state is going to go through a set of Grover iterations which will make it closer to the desired state. Here's what you get. From 0.15625, because now I'm using 6 qubits here just to get statistical results. So this is a larger number of items. From the classical probability of 1.5%, I'm up to a probability of finding the result of 60%. This kind of approach is an approach that we call amplitude amplification. This is fabulous because I've done it without looking into the internal state of my qubits. Yet I've managed to get an absolutely impressive result. So the immediate question is, how do you create something like this? Right? Well, it has been already answered by Professor Marcus's keynote, right? The only thing that I want to emphasize here is that all of these in real life work at 0.03 Kelvin, which is 30 millikelvin, given the fact that the coldest place in outer space has a temperature of around 3.5 Kelvin. Imagine the challenge of building something like this. The one thing that amazes me about Microsoft with respect to quantum computing is the courage and vision that the quantum team has when it comes to creating a quantum computer. Because the way they build their quantum computer is fundamentally different from all the others on this planet. The reason why they do it is because topological quantum computing, which is the approach taken by Microsoft, promises much, much more stable qubits. So when you hear today the IBMs and the Googles and the Rigettis of the world saying, we have 50 qubits, we have 70 qubits, moving from 70 to 1,000 is practically impossible using the other approaches. And you really have to have vision and courage to approach this the way Microsoft approaches. And that is the end of our story today. So the way I see the world developing in the next decade or decades, we will still have amazing improvements in classical computing. And quantum computing is not going to replace classical computing. It's going to enhance and is going to provide solutions to some of the intractable problems that classical computing cannot solve today. But in the same time, what we will see in the space of quantum computing is simply going to be mind-bending. And that, my friends, is also a huge challenge for all of us. Because I hope that from this glimpse that I've shown you today, you will see the challenge of thinking in terms of quantum computing. You actually have to forget almost everything that you know about computing and reset your mindset. So with that, I thank you very much for today. I'm truly honored and humbled to see you in such a great number. I hope all of what I've said makes a lot of sense. If not, I hope it will make at some point. You can find me on my website. And I'm also very, very happy and honored to announce that this December, we're going to have the first dedicated AI Microsoft conference. It's going to run in Vegas between the 3rd and the 6th of December. It has an amazing lineup of speakers, and of course, I'm talking about the first line, obviously, right? So if you feel like gambling a little bit, come see us in Vegas this December. Once again, thank you very, very much. And also, if you liked it or if you've hated it, please rate it on your mobile app. Thank you very much.